Let u, v, and w be vectors in a vector space V, and let C be any scalar. An inner product in V is a function that associates a real number, inner product of u and v, with each pair of vectors u and v, and satisfies these four axioms. Inner product of u and v is equal to the inner product of v and u. In other words, the inner product is commutative. The inner product of u with v plus w is the inner product of u with v plus the inner product of u with w. C times the inner product of u with v is equal to the inner product of c times u with v. And finally, the inner product of v with itself is always greater than or equal to 0, with equality holding if and only if v is equal to the identity. When dealing with the vector space Rn, the most common inner product is called the dot product of vectors, and we call this the standard inner product. Now here's how the dot product is defined. Right? So inner product of u with v, u1 v1 plus u2 v2 plus u3 v3 plus so on and so forth plus un vn. In other words, take the products of corresponding components and then sum all those products up. It is left as an exercise to the viewer to verify that this satisfies the four axioms that were listed previously. Here we look at a less conventional inner product. So we're going to consider two vectors in R2. We're going to show that the inner product defined as u with v is u1 v1 minus u2 v1 minus u1 v2 plus 3u2 v2 defines an inner product. So remember, what we have to do is we have to show that it satisfies these four axioms. All right? So starting with the first axiom. We take u with v. Right, by definition, this is u1 v1 minus u2 v1 minus u1 v2 plus 3u2 v2. However, u1, u2, v1, v2 are all real numbers. And we know that multiplication of real numbers is itself commutative. So we can rewrite this as v1 u1 minus v1 u2 minus v2 u1 plus 3 v2 u2. Also, addition and subtraction of real numbers is commutative. So what we can do is we can take this negative term here, and switch their order, which allows us to write v1 u1 minus v2 u1 minus v1 u2 plus 3 v2 u2. And if you notice, this is now exactly the definition for the inner product of v with u. Second axiom, we want to take u with v plus w. So we get u1 and then times v1 plus w1, then minus u2 times v1 plus w1 minus u1 times v2 plus w2 plus 3u2 times v2 plus w2. Okay, now, again, these are all real numbers. And we know that real numbers multiplication distributes across addition. Addition of real numbers is associative, so we can group however we want. Well, why not group all of the terms that involve v's? That'll give us this. And then we can add that to the grouping of the terms that involve the w's. This first grouping is precisely the inner product of u with v. That second grouping is precisely the inner product of u with w. Right, well, that proves the second axiom. Third axiom. Take any real number, let's call it k, multiply it with the inner product of u with v. So this would be k times this we can distribute that k through. Multiplication of real numbers is also associative. So we can group like this. And this is precisely the inner product of ku with v. Right? So the third axiom is satisfied. Fourth and final axiom. Let's go ahead and take the inner product of u with itself. Right, well, we're going to have u1 squared. Now notice those two middle terms are identical. And this is because multiplication of real numbers is commutative. And that final term will be plus 3u2 squared. Since we're dealing strictly with real numbers, we know this will always be non-negative. Right? So for all u1, u2, this is always greater than or equal to 0. Also notice, if u1 squared plus 3u2 squared is equal to 0, then what we get is u1 squared has to equal negative 3u2 squared. And there's only one way this is possible. There's only one way for a square to equal a negative number times a square. And that's if both of those numbers are 0. So we get the fourth axiom being satisfied, which is all we needed, so this does indeed define an inner product. A vector space that has an inner product defined on it is called an inner product space. Take three vectors u, v, and w in an inner product space and take c to be any real number. And then the following three statements hold. First is that the inner product of the identity with v is equal to 0, right? And remember, since it's commutative, 0 with v and v with 0 are obviously identical. Inner product of u plus v with w is the inner product of u with w plus the inner product of v with w. Notice that this is just the flip of axiom number 2 in the definition. And finally, the inner product of u with cv is equal to c times the inner product of u with v. Once again, notice that this is just the flip of axiom number 3 in the definition. In the proof, we shall only prove this first statement. The other two are fairly simple. I've already explained sort of how to do it. And so that will be left as an exercise for the viewer. So first, by definition, we have the inner product of 0 with v is equal to the inner product of v with 0, as was mentioned. Now let's just show that the inner product of 0 with v has to equal 0. Well, recall by definition that the 0 identity is just 0 times v, right? So this becomes the inner product of 0 times v with v. And then we can write it as 0 times the inner product of v with v. But remember, by definition, the inner product of v with v is a real number. So 0 times any real number is itself 0. Right? So that proves the first property, and as was stated, the remaining two statements will be left as an exercise. We now look at some measures of inner product spaces. So we take two vectors u and v in an inner product space v. The norm of u is defined to be the square root of the inner product of u with itself. The distance between u and v is the norm of u minus v. The angle between two non-zero vectors u and v can be found by using the relation cosine of theta is equal to the inner product of u with v all over the norm of u times norm of v. And we take theta to be between 0 and pi. Finally, we say that u and v are orthogonal when the inner product of u with v is equal to 0. We now look at three famous results. The first is called the Cauchy-Schwarz Inequality, and just in terms of numbering, this should be Theorem 2. Alright, so Cauchy-Schwarz Inequality says if u and v are vectors in an inner product space, then the absolute value of the inner product of u with v is less than or equal to the norm of u times the norm of v. Well, we call that we have cosine of theta is the inner product of u with v over norm of u times norm of v. All right, well, this would mean, of course, that norm u, I'm going to write it this way, that the inner product of u with v is equal to norm of u times norm of v times cosine of theta. All right, well, this would mean that if we take the absolute value of both sides, we get this, which is equal to, remember, with absolute values of real numbers, if you take an absolute value of products, it's just the product of the absolute values. All right, well, norm of u and norm of v, they're always non-negative. So we actually don't need their absolute values. Also recall that the absolute value of cosine of theta is less than or equal to 1. So I can replace the equals here with a less than or equal to. And write, because the absolute value cosine of theta is always less than or equal to 1. Notice that this now proves the Cauchy-Schwarz inequality. The second result is the triangle inequality, and again, numbering is off. This should be number 3. Triangle inequality states, let u and v be vectors in an inner product space, then the norm of u plus v is less than or equal to the norm of u plus the norm of v. What we will do is take a look at the norm of u plus v squared. Right, this would just be the inner product of u plus v with u plus v. Right? What we're going to get is norm of u plus v with u plus the norm of u plus v, inner product of u plus v with u and plus the inner product of u plus v with v, which will give us the inner product of u with u plus the inner product of v with u plus the inner product of u with v plus the inner product of v with v. Right, we can write the inner product of v with u as the inner product of u with v. So notice now what we have is the inner product of u with u plus 2 times the inner product of u with v plus the inner product of v with v. Now, we already know that the inner product of u with u is the norm of u squared. We also know that the inner product of v with v is the norm of v squared. And what we can do is use Cauchy-Schwarz inequality to write the inner product of u with v as less than or equal to the absolute value of the inner product of u with v. I'm sorry, that wasn't using the Cauchy-Schwarz inequality. That's just a simple fact. right? Any real number will always be less than or equal to its absolute value, right? Because it's either going to be a positive number, in which case it's going to equal its absolute value, or a negative number, in which case it'll be less than or equal to, or less than its absolute value. Now using Cauchy-Schwarz, this can be written as 2 times norm of u times norm of v. And notice what this is. This is equal to the quantity norm of u plus norm of v squared. So what we've just shown is that the norm of u plus v squared is less than or equal to the quantity of the norm of u plus the norm of v, all squared. Taking the square root of both sides, we get our desired result. The third result is called the Pythagorean Theorem. And again, numbering is off. This should be theorem number 4. Pythagorean Theorem, let u and v be vectors in an inner product space. Then u and v are orthogonal if and only if the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. The proof of this result is fairly straightforward. It uses the triangle inequality as well as the definition of orthogonality. And so the proof of the Pythagorean theorem will be left as an exercise to the viewers. Let u and v be vectors in an inner product space V such that V is not the identity. Then the orthogonal projection of u onto v is the norm of u, the inner product of u with v over the norm of v squared all times v. And notice how it's represented. We're looking at the projection of u onto v. So it's projection sub v of u, right? Projection of u onto v. So whatever you're being projected onto is your subscript.